LangGraph's checkpoint management system employs a PostgresSaver class to persist workflow state in a PostgreSQL database, using structured configurations to isolate thread-specific data and version channel values. This implementation demonstrates the core pattern of initializing a database-backed checkpointer, storing and retrieving state snapshots, and enumerating available checkpoints through a clean interface. We'll examine how the connection string establishes database access, how the setup method prepares the storage schema, and how the put, get, and list operations manage checkpoint lifecycle with thread-scoped configurations. The code reveals the practical sequence of database initialization, state persistence, and retrieval that underpins reliable workflow resumption. From LangGraph, checkpoint, Postgres import PostgresSaver. Write config equals configurable. Threaded, 1 checkpoint ns. Read config equals configurable. Threaded, 1. db URI equals Postgres. //Postgres. Postgres at localhost. 5432/Postgres. SSL mode equals disable. With PostgresSaver, from constring db URI as checkpointer. Hash call setup the first time you're using the checkpointer. Checkpointer setup. Checkpoint. V4. TS 2024-07-31T 2019. 804,150 plus 0000. ID 1F4F797-8035-6428-8001-8A1503 F9B875. Channel values. Mikey, meow. Node. Channel versions. Start 2. Mikey 3. Start node 3. Node 3. Version seen. Input. Start 1. Node. Start node 2. Hash store checkpoint. Checkpointer, put write config checkpoint. Hash load checkpoint. Checkpointer, get read config. Hash list checkpoints. List checkpointer, list read config. This code demonstrates the practical use of PostgresSaver for checkpoint management in LangGraph, showing how to persist and retrieve workflow state in a Postgres database. The pattern follows a clear sequence. First establishing a connection via from constring, then initializing the database with setup, and finally using the core checkpointer methods put, get, and list to manage checkpoints. The write config and read config dictionaries illustrate how thread-specific state is handled, with threaded acting as the primary key for checkpoint isolation. The checkpoint structure itself reveals LangGraph's versioning system, where channel values store the actual state like my key, meow, while channel versions and version scene track update history for each channel. This design enables precise state recovery and conflict resolution in distributed workflows. The explicit setup call is noteworthy. It ensures database tables exist before operations, which is critical for first-time usage, but can be skipped in subsequent runs. Using Postgres as a checkpoint store provides durability and scalability compared to in-memory alternatives, making it suitable for production workflows that require persistence across restarts. However, this introduces dependency on a database and slight latency overhead. The code also highlights the separation of concerns. Connection management, from constring, schema setup, and state operations, put/get, which aligns with LangGraph's modular design for checkpointing. Let's break it down. From LangGraph, checkpoint, Postgres import PostgresSaver. Imports the PostgresSaver class from the LangGraph. Checkpoint, Postgres module, which provides checkpoint persistence functionality using PostgreSQL as the storage backend. This class enables saving and retrieving workflow state checkpoints from a PostgreSQL database.
Write config equals configurable. Threaded 1 checkpoint ns.
Creates a dictionary named writeConfig with a nested structure containing a configurable key. This nested dictionary holds two string values, threaded set to 1 and checkpoint ns set to an empty string. The structure suggests configuration for thread-specific operations with checkpointing capabilities, though the actual usage isn't visible in this segment.
Read config equals configurable. Threaded 1.
Creates a dictionary named readConfig with a nested structure containing a configurable thread ID set to 1. This appears to be setting up configuration parameters where the thread identifier is explicitly defined for whatever process will use this configuration.
dbURI equals Postgres //Postgres, Postgres at localhost 5432/Postgres, SSL mode equals disable.
Assigns a PostgreSQL connection string to the variable dbURI that specifies the database location, credentials, and connection parameters. The string indicates a local PostgreSQL server running on port 5432 with username and password both set to Postgres, targeting the Postgres database, and explicitly disables SSL encryption for the connection.
With PostgresSaver, from constring dbURI as checkpointer.
Creates a context manager for a PostgresSaver checkpointer instance using a database connection string. The fromConString class method initializes the checkpointer with the provided dbURI, and the with statement ensures proper resource management by automatically handling setup and teardown of the database connection.
Hash call setup the first time you're using the checkpointer. Checkpointer setup.
Calls the setup method on the checkpointer instance to initialize the database store, creating necessary tables and running migrations if this is the first time the checkpointer is being used. This is a required one-time setup step before the checkpointer can be used to persist workflow state.
Checkpoint equals.
Initializes a dictionary variable named checkpoint with an empty dictionary literal. This creates a mutable container that can store key-value pairs, likely intended to hold checkpoint data for state persistence in a LangGraph workflow. The dictionary is currently empty, with no initial key-value pairs defined.
TS 2024-07-31T 2019 804,150 plus 0000.
Assigns a timestamp value of 2024-07-31T 2019 804,150 plus 0000 to a key TS in what appears to be a dictionary or JSON structure. The timestamp follows ISO 8601 format with microsecond precision and UTC time zone offset.
id 1F4F797-8003-6001-8A1503 F9B875.
Assigns a UUID value 1F4F797-8335-6001-8A1503 F9B875 to the key id in what appears to be a dictionary or JSON structure. This establishes a unique identifier for the associated entity or record.
Channel values.
Defines a dictionary key named channel values that will contain a nested dictionary structure. This appears to be part of a configuration or state object where channel values are stored, likely for communication between actors in a LangGraph workflow. The opening brace indicates the start of this nested dictionary definition.
MyKey, meow.
Assigns the string value meow to the key MyKey in what appears to be a dictionary or state object, establishing an initial state value that can be updated by nodes in a LangGraph workflow.
Start 2.
Sets the starting node for the graph execution to node 2, where start is a special key indicating the entry point, and the value 2 specifies the node ID to begin processing from.
MyKey 3.
Assigns the integer value 3 to the key MyKey in a dictionary, establishing an initial state value that can be updated by nodes in a LangGraph workflow.
Start node 3.
Assigns the value 3 to the key start node in what appears to be a dictionary or JSON-like structure, indicating that node 3 is designated as the starting node in a graph traversal or workflow execution.
Node 3.
Assigns the integer value 3 to a key named node in what appears to be a dictionary or JSON-like structure. This establishes a node identifier or reference point within the graph configuration, though the specific usage context isn't visible in this isolated segment. The value suggests this might represent a node position, index, or identifier in a graph workflow.
Start.
Defines the entry point of a LangGraph workflow with the key start as the initial node. This establishes the starting position in the graph's execution flow, where processing will begin when the workflow is invoked. The empty dictionary indicates this is a node definition placeholder that will be populated with actual implementation details elsewhere in the configuration.
Start 1.
Sets the initial value of the state key, MyKey, to 1 in a LangGraph workflow. This establishes the starting point for stateful operations where nodes will update this key as the graph executes.
Start node 2.
Assigns the value 2 to the key start node in what appears to be a dictionary or configuration object. This sets the starting node identifier to node number 2 for the graph execution.
Checkpointer.put write config checkpoint.
Calls the put method on a checkpointer instance to store a checkpoint with the specified write configuration, checkpoint data, and empty metadata and tags dictionaries. This persists the current state of the workflow for potential later retrieval or resumption.
Checkpointer.get read config.
Calls the get method on a checkpointer instance, passing read config as the parameter to retrieve a checkpoint based on the provided configuration. This operation fetches the persisted state associated with the specified configuration, allowing the workflow to resume from a previously saved point.
Hash list checkpoints. List checkpointer, list read config.
Calls the list method on the checkpointer object, passing read config as an argument, then converts the returned checkpoints into a list. This retrieves and displays all available checkpoints based on the provided configuration. The PostgresSaver implementation demonstrates LangGraph's modular checkpointing pattern, where database-backed persistence enables reliable workflow resumption. The sequence begins with connection establishment via from constring, followed by schema initialization through setup, which is critical for first-time usage. The core operations, put, get, and list, then manage the checkpoint lifecycle with write config and read config, ensuring thread isolation via threaded. The checkpoint structure itself reveals LangGraph's versioning system, where channel values store state like MyKey, meow, while channel versions and version scene track update history. This design supports precise state recovery in distributed workflows. Using PostgreSQL introduces durability and scalability, but adds dependency overhead compared to in-memory alternatives. The separation of concerns, connection management, schema setup, and state operations aligns with LangGraph's modular design, making it suitable for production workflows requiring persistence across restarts.
The checkpoint leaps into Postgres with a splash, but the query only finds ripples.